All right, good morning, class. This is lesson 15, covering section 4.2 of our textbook. So we're continuing in chapter 4 now, where we've been talking about vector spaces, and we've just been introduced to what it means to be a subspace. But in particular, when we're solving the matrix equation, or in general, when we're talking about the matrix equation at all, there are some special subspaces which are associated with the matrix equation. And looking at these subspaces can often give us other information about the matrix equation, which can sometimes be helpful, depending on what the problem is we're trying to solve. So we want to go back and look more at the matrix equation. I mean, as we said from day one of this class, the matrix equation is like everything in this class, and we just keep coming back to it, and we keep looking at it in a new light, looking at it through a new lens with some new vocabulary or some new idea, so on and so forth. We're going to be doing this for the rest of this class. It really is what Intro to Linear Algebra is all about. Okay, so what are we talking about? 4.2, we're looking at the matrix equation, which we already know lots of different methods for solving it. That's fine. But what we can now see is that when we do solve for a solution set, that itself is also a special subspace. So what do I mean? Well, AX equals B can be solved for sometimes multiple solutions. When do we have multiple solutions? When we have free variables, right? So we already know this. This isn't new. But in particular, one class of matrix equations is the homogeneous system. So we're going back to this idea of a homogeneous system, which is just a matrix equation which has been set equal to 0, right? So we know for this kind of system, there is always a solution. In fact, the trivial solution is always a solution. When x is 0, you plug in a 0 vector for x, multiply it, you're going to get 0, right? So this always has at least one solution. In fact, if I were to think about the set of solutions for the homogeneous system, well, if only trivial solution, then that means my set contains only the 0 vector. All right, so this is a small set. In fact, it's a finite set with only one vector in it. But in fact, while it's kind of a funny example, this is a subspace. Why? Well, first of all, it has a 0 vector. Check, that works. Requirement 2 to be a subspace. For any vectors in this set, if I add them together, it has to stay in the set H. Well, 0 plus 0 is the 0 vector still. So yeah, no matter what I add in here together, there's only one vector to add together. It's still going to stay in here. So that checks number 2. Number 3, what happens if I scale the 0 vector? Well, no matter what real constant you pick, c times the 0 vector is still the 0 vector. So in fact, this is what is called like a trivial example of a subspace because it only has the 0 vector in it, right? And so now that we're starting to narrow in on this kind of subspace, this type of subspace actually has a special name. So what we call it is the null space. Is the set of solutions for the homogeneous system, right? So this is specifically what the null space is. If your matrix is not set equal to 0, the null space does not exist, right? The null space is only the set of stuff that when you plug it in, you get out the 0 vector, right? This is only what the null space is. But more specifically, we have this trivial example of a null space where it only has one vector in it. But what if A ends up having a free variable? Then we have non-trivial solutions, and the null space gets bigger. Okay, well, what's an example of that? Well, in particular, we can think about the case where A equals 1, -3, 2. Oh, sorry, -2. -5, 9, 1. And we want to set it equal to the 0 vector. So we're talking about a homogeneous system. So when we're trying to find the null space of A, the null space of A is the set of X that when I multiply it with A, I get out 0, right? In other words, the null space is another way of saying I want to find the solutions to the homogeneous system. Okay, so again, this isn't a new problem. We know how to solve this. We've done this before. What's new is that we're now applying new vocabulary to it, right? Okay, so we know how we can solve this problem. We augment and we row reduce, right? We know how to row reduce at this point, or we should. So for the sake of time, I'm just going to go ahead and write down the row reduced echelon form. And we're going to have 1, 0, 2.5, 0, 0, 1, 1.5. And lo and behold, we have a free variable now. X3 is free. All right. So just like before, we can now write this solution set in parametric form and then write this solution set as the span of something. All right, so let's see how this works out. So first of all, what's my x2? x2 equals -1.5 x3. All right, what about x1? x1 equals -2.5 x3. Great. So my vector x, the set of all possible solutions, looks like this. And if I factor out the x3, that means every single possible solution for this homogeneous system is some multiple of this vector right here, right? So this is what is going to give us our null space. In fact, the set of all possible solutions here, and I'll go ahead and introduce the notation. When we're talking about null spaces, we're going to write NUL for null. And this is the null of A, the null space of A. This is the set of solutions to the homogeneous system. What is it? It equals the span of this vector, right? It equals the span of this vector. Why? Well, it's any possible multiple of this vector. It's any possible linear combination of this vector. Well, if you have a set which is all possible linear combinations, you're talking about the span. So this null space is the span of a vector. And we already know from yesterday, anytime you have a set which is the span of something, that is automatically a subspace. What is this a subspace in? This is a subspace of R3, right? Why is it a subspace of R3? Because my vectors for X are in R3, right? This is a subset of R3. It is not all of R3. This null space is not three-dimensional because I only have one direction I can move in. So we want to be very careful here. Dimension and the space you are in are two separate things. They're separate ideas. This null space is not three-dimensional. I want to highlight this because every semester students make this mistake. The null space is not three-dimensional because it only has one vector in the span. That means there is only one direction the null space can move in. And so this null space is one-dimensional. Why is it one-dimensional? Well, if you graph this, what does it mean to take the span of a single vector? Okay, well, a single vector in R3, that's some line in R3. And I can take any multiple of that line. I can stretch it out in a positive direction. I can stretch it out in a negative direction, right? But no matter what I multiply it by, I stay on the line. Well, a line is one-dimensional in that you only have one axis you can move along, right? Think about like the real number line. The real number line by itself is a one-dimensional space. A line is a one-dimensional space because there's only one axis. Now, it just so happens that this line exists in R3. So this is a subspace of R3, but the subspace is not three-dimensional. It's just a line that's inside of R3. So it's a one-dimensional subspace that is inside of R3, right? So I want to be really clear about that here. Okay. So we can now clarify our definition here. We can also see examples of where a null space can be a space with only a single vector in it, or it can be a space with infinitely many vectors in it. And there's no in between. The null space can never be empty because you always have the trivial solution. So again, the null space can never be empty. All right. So let's write out a formal definition then for null space. We then have if A is an M by N matrix. And note here, we're no longer talking about square matrices. In chapter 3, we only talked about square matrices because it's only for square matrices which can be invertible, right? But chapter 4, we're not so concerned with invertibility anymore. Instead, we're just talking in more general terms about vector spaces and null spaces. We can have a null space for any size matrix because, again, the null space is just the set of solutions to the homogeneous system. All right. Then the null space of A, first of all, is a subspace of Rn. Why is it in Rn? Well, remember, if A is an M by N, so imagine over here the equation. If A is an M by N, that means X has to be an N by 1. And if the null space is a set of X's, and these X's have N entries, that means these X's are in Rn. So the null space is a subspace of the domain. This is a key point here, and we're going to draw a picture of this in just a moment. The null space is a subspace of the domain. All right? More specifically, for notation's sake, the null space of A, using this notation, equals the set of X vectors in Rn such that A times X equals 0. Again, it's the set of solutions to the homogeneous system. So this is always not empty because at the very least, the 0 vector is always in here. All right. Right. Okay. So we can also look at some other funny examples. And in fact, I think there's a homework problem that does this. So we can talk about how to solve this kind of question. So here's an example. Suppose let's let H equal the set of vectors A, B, C, D. Notice this is in R4 such that, and we're given some equations. D equals A minus 2B plus 5C, and B equals C minus A. Okay, how are we supposed to go about this problem? So first, I want to note, we can't just plug in D equals and B equals. Why? Because these have a mixture of each other, right? B equals C minus A. D has this B inside of the equation. So we can't just plug it in unless you replace that B. But that's going to get messy, and that's really kind of the hard way to do this problem. What can we do instead? Well, this is a set of vectors such that it satisfies these two equations, right? So what I could do is, what if I just move everything to the same side? I'm going to subtract everything over, and we have negative A plus 2B minus 5C plus D equals 0. Negative C, and I'm intentionally writing it in a different order so that you can see what's happening here, plus B. Right? I subtracted everything over. And so what's happening, the vector A, B, C, D is really, this is a set of solutions to this equation. Well, what is this equation? This is a homogeneous system. Why? Because it's set equal to 0. Was this originally set equal to 0? No. But I can take these equations and rewrite them in a way such that now this is a homogeneous system. Okay, but how does that help us? Well, now that I have this written as an equation, we can notice, all right, I have a coefficient matrix. This is my matrix A. And I have 2 rows, right? I also have a B. My B is equal to the 0 vector. In other words, these vectors A, B, C, D, these are the set of vectors such that when you multiply it with matrix A, you get out 0, right? A, B, C, D is the set of solutions to this homogeneous system. Well, in other words, what is H? H equals the null space of A. Even though that's not how H was first described, even though the way this is first written doesn't tell us anything about null spaces, we can rewrite this in a way and finagle it to get it into a format where we can see, oh, actually, this H, it's a set of solutions for this homogeneous system. It's the null space of this matrix A. Well, now I can rewrite H as the span of some solutions. Okay, so next I got to find the solutions, right? So how do we do that? We need to row reduce the augmented matrix. So let's see, let me make some space here. So we're going to augment we're going to row reduce the augmented matrix. So for the sake of space, I'm just going to write out A. I'm going to augment with B, which is, the 0 vector. And then again, for the sake of space and time, I'm just going to go ahead and row reduce this with a calculator. And we're going to get a row reduced form of 1, 0, 3, 1, 0, 0, 1, -4, -1, 0, right? And we see, okay, I got a pivot, but So remember, now we're using A, B, C, D, because that's what my vector X is. And we see that C and D are free. All right. Oh, let me make sure that's still on the screen. It is. Great. So what's the next step? I need to figure out what my vector is. Okay, well, what's B? B equals, if I add these over, 4C plus D, and A equals negative 3C minus D. And now I can construct what this vector is. H is the set of these vectors that make this happen. In other words, H is the set of vectors A, B, C, D, which equals negative 3C minus D, 4C plus D, C and D, because those are the free variables. And so just like we did back in chapter 1 or chapter 2, we can rewrite these solutions in parametric vector form. Right? So parametric vector form was not just something we were doing for that one time. We're going to need it a lot as we continue in the class. Plus D times negative 1, 1, 0, 1. Right? In other words, these vectors, this vector ABCD is any linear combination of these two vectors. C and D can be any real numbers. This is any possible linear combination of these two guys. So what is H? Well, not only is H the null space of A, like we said earlier, but it's also the span of these two vectors, negative 3, 4, 1, 0, and negative 1, 1, 0, 1. Right? And again, we can note this is a subspace of R4. Why? Because these vectors are four-dimensional. These vectors have 4 entries. But again, this null space is not 4-dimensional. The null space of A is not a 4-dimensional space because now I only have 2 directions I can move in. I only have 2 axes. This null space is 2-dimensional because there are 2 vectors in the span. So this null space is a 2-dimensional subspace of R4. Okay, well, what does that actually mean? Well, what is a 2-dimensional space? You can think like R2. You have an x-axis direction you can move in. You have a y direction axis you can move in, and that's it. In other words, what is a 2-dimensional space? A 2-dimensional space is a plane. So this null space is a plane of vectors that is inside of R4. This is a plane inside of R4, right? So this is a 2-dimensional subspace of R4. Again, it is not 4-dimensional. The dimension of a space is the equivalent to the number of vectors you have in your span, or at least the number of linearly independent vectors in your span. When you're solving for solutions of a null space like this, these are always going to turn out to be linearly independent. But when we start talking about other spaces, we have to be a little bit more careful. And we'll see that actually in just a moment. All right. So this is going to sum up null space for us. But there are still some other subspaces we can talk about with regard to the matrix equation. Okay, so what else can we do? All right. So we have another type of space. I'm just going to give you the definition, and then we'll talk about some examples. So again, A does not have to be square. If A is an m by n matrix, then the column space of A is the set of all possible linear combinations. So here's the key: set of all possible linear combinations. That tells you, oh, we're talking about the span of something. The set of all possible linear combinations of what? The columns of A. Right? We're looking at the column space, so we're looking at all possible linear combinations of the columns of A. In other words, if A has one column, two columns, AN columns, right, and these are columns, then the column space of A equals the span of the columns, right? And we already know from yesterday's class that anything which is the span of something is automatically a subspace. But what is this a subspace of? Well, these vectors, these column vectors, each column vector has m entries because there are m rows in the matrix. Each column has m entries. This is a subspace of Rm. In other words, the column space is a subspace of the codomain. Codomain for our matrix equation, right? It's the set of possible outputs, right? Remember, when we had our matrix equation, AX equals B, what is B? Well, B is an output of doing A times X. What is A times X? A times X is a linear combination of the columns of A. In other words, the column space, it's the set of all possible B. It is the set of all possible outputs of the matrix equation. It is the set of all possible outputs from A times X, right? So we can alternatively write the column space. It is equal to the set of any possible B in Rm, my codomain, such that AX equals B for some X in my domain, Rn. Right? So this is saying it's a set of all possible outputs. Pick your favorite X, multiply it with A. Whatever you get from the result of that multiplication, that's in the column space. But you can do that for any X in your domain. Plug it in, that gives you a new output. The column space is the set of all possible outputs, right? So the column space as well, we can rewrite as the span of something. Now, what's one key difference between the null space and the column space? Well, the null space, when we're solving for the solution set, we get linearly independent vectors. However, if I'm just looking at all of the columns of A, all of those columns are not necessarily linearly independent, right? If my matrix A has a free variable, then one of my columns is not independent. So in fact, when we have dependent vectors, we can just throw them out and ignore them. And we'll look more at this in just a moment. But before I get more into that, well, actually, you know what? Let's go ahead and talk about this. Let me make some space. So what do I mean by we can throw out the dependent vectors? All right. Well, first of all, let's suppose my matrix A is 1, 0, 2, 0. All right, so we're going to stay in R2, so it's easy to draw. Now, we know by definition here, what is the column space? Well, the column space is the span of the columns, 1, 0, and 2, 0. Okay, so there's nothing wrong with this answer. I mean, this answer is technically correct. However, what's happening here when I take linear combinations of 1, 0, and 2, 0? Well, 1, 0, okay, that's right here, right, on the y-axis. Or no, sorry, this is in the x-axis. Let me draw this correctly. 1, 0 is going in the x direction. Right? And then, but because I'm taking the span of it, that means I can take any multiple of 1, 0. I can stretch it out to 2, 0. 2, 0 is already included. I can stretch it out to 3, 0. I can stretch it out the negative direction as much as I like. I can go anywhere on the x-axis just with the vector 1, 0. Well, what does the vector 2, 0 do? That says, well, I can go out to 2, 0. Okay, but I can already do that because 2, 0 is already on the x-axis. In other words, we can look here at the picture, or at the matrix, rather. Column 2 is not linearly independent because column 2 is really just a multiple of column 1. So do we need to include column 2 in the span? No. This vector 2, 0, 2, 0 equals 2 times the first column. So if I can rewrite this as just the span of 1, 0, and I haven't changed anything. Why? Because 2, 0 is already in here because it's a multiple of 1, 0. So it's in the span of 1, 0. So what I'm getting at is, it's true the column space is the span of all the columns, but we actually don't need all of the columns. We only need the linear independent columns. We only need the columns which have a pivot. So this gets to a key point here. All right, what is the dimension of the column space then? Well, this is a subspace of R2, but now that I've narrowed it down, so I'm only looking at the independent columns, this column space is one-dimensional, right? Even though I started with 2 vectors in the span, I actually don't need both of them because the second one is really just a multiple of the first. It doesn't add a new axis, right? Even though I have 2 vectors originally in this span, I still only have one axis I can travel on. Well, if I only have one axis, then it is one-dimensional. Now, another key point I want to make, because I've seen some students making this mistake. Some students have talked to me about this. One-dimensional, this does not mean we're equal to R1, right? This does not mean we're equal to R1 because these vectors are still two-dimensional. These vectors still exist in R2, right? This does not equal R1. It does not equal R2. It is a one-dimensional subspace of R2. So this is a very key kind of point to get the vocabulary straight in your head. The span of a single vector that is a one-dimensional space, but being one-dimensional does not mean you equal R1. Being two-dimensional does not mean you equal R2, right? Just like our earlier example, I erased it, but we had that H, which was the span of 2 vectors in R4. That was a two-dimensional subspace, but it does not equal R2. It is a plane like R2, but it was a plane that exists in R4, which says that it is not R2 at all, right? Just as while this is a line that exists in R2, it's not R1 because it is a line in R2, right? R1 doesn't exist in R2. R1 is just a line. There is no plane to put the line on. It's just a line. So when you have a line in R2, that is not equal to R1. It's a separate one-dimensional space. So again, the dimension of your space has nothing to do with what R we're talking about, right? So I want to really nail down this point because a lot of students make this mistake. The dimension of the space has nothing to do with what R you're in. Okay. Now there are some limitations on dimension, which relates to R in some ways, but we're gonna talk about that more later in chapter 4. I don't want to confuse you too much yet. All right. So great. We had this example of a column space. But now I want to really emphasize the difference between column space and null space. All right, and let me just double check something real quick. Yeah, okay. Yeah, there's some things that are coming later in chapter 4, so I won't talk about all of this. Some of this we're going to talk more about actually in tomorrow's lecture. All right, so null space versus column space. What's the difference? All right. Well, first of all, like we said earlier, let's start with, let's say A is an M by N matrix. All right. Then we can say T is the transformation on X, which multiplies A times X. A is the standard matrix, right? And this results in some kind of output vector. Okay. Well, what is my domain? My domain is Rn. My codomain is Rm. I plug in a vector that's in Rn. It gets multiplied by A, and it outputs a vector in Rm. All right. So imagine that this is our domain. This is Rn. What then is the null space? Well, we said earlier, the null space is a set of inputs. It's the set of x's which get mapped to the 0 vector. So the null space, well, it's this thing inside of my domain, right? It's inside of my domain. It could possibly be all of the domain if you have some kind of transformation which just turns everything into 0. But whatever it is, the null space is just the set of things where, if we look at the codomain, Rm, this is my set of the codomain. The null space, this is the set of stuff that when I plug it into my transformation, when I multiply it with matrix A, it results in the 0 vector, right? So this 0 vector is a possible output. All right. Now, what is the column space? We said that the column space is all possible linear combinations of the matrix A. In other words, it's the set of all possible ways you can multiply A times X. It is the set of all possible B. Now, remember, as we've discussed before, your set of all possible B may or may not be all of the codomain, right? Because it could be, maybe there's some B that we don't have a solution for. Maybe there's some B in Rm that a solution does not exist, right? There could be some B out here, which there's no X that maps to it. There's no solution for that B, right? In which case, the column space is not everything in the codomain, right? So there might be some special B which has no solution. B star has no solution. But the column space does include other b's. Maybe there's a b1 or a b2 or a b3 or infinitely many b's in here. The column space is the set of all possible b's which do have a solution. All possible b's which have an x that gets mapped to it, right? So this column space, it's not necessarily all of the codomain, but sometimes it could be all of the codomain. When is it all of the codomain? Well, exactly when my transformation is onto, right? So again, those vocabulary terms we discussed in, what was it, chapter 2, they're going to come back, right? We can continue tying in everything we've talked about in this class. Everything kind of ties together in some way. Okay. So the column space is not necessarily all of the codomain, but if my transformation is onto, which again, remember, that means I have a pivot in every row. If I have a pivot in every row, then the column space does equal all of the codomain. If I don't, then the column space is a subspace of the codomain. It's strictly a subset. All right. So some things that we can note about this. Let's see. I might be able to make space down here, actually. Let's see. Let me make sure this doesn't go off the screen. Oh, yeah, we got space. OK. So some notes here. First of all, one, the column space of A, as we've discussed, it's the set of possible outputs. In other words, it is the range of T, since the range is the set of outputs. All right. 2, if the null space has more than one vector, then T is not one-to-one. Okay, well, what does that mean? Well, remember, one-to-one, this is this notion of for any possible output, we only have one x that maps to it, right? One-to-one is the same idea as the horizontal line test for functions. One-to-one says, yeah, no matter what two things I plug in, no matter what two x's I plug in, they can never map to the same place. So you can imagine, well, if you have two different vectors in the null space, which get mapped to 0, you just broke one-to-one, right? So being one-to-one means your null space has only the trivial solution. This is going to be a key thing, and we're going to highlight column space and null space for the invertible matrix theorem. We're going to do that later. We're not going to do that today just for the sake of time. I don't want to overload with information. So T is not one-to-one if this null space has more than the 0 vector, if it has more than one vector. All right. And then thirdly, if the column space does not equal all of the codomain, which can happen, maybe there's some B which doesn't have a solution, then T is not onto. So again, we're seeing that this null space and column space, these subspaces associated with the matrix equation, have special relationships with one-to-one and onto. And again, we're going to highlight these relationships more so when we start talking again about the invertible matrix theorem. We're going to come back to that, but we're going to do that later, not today. All right. So there's one last subspace I want to introduce real quick, and then we'll talk about today's participation question. So we've talked about a null space. We've talked about a column space. Well, the matrix A, though, not only does it have columns, it also has rows. So if we can talk about a column space, we can also talk about a row space. All right. So again, A does not have to be square. If A is an m by n, matrix, then the row space of A is the set of all possible, so the same definition we saw before, except now we're doing it for rows, all possible linear combinations of the rows of A, right? So if the matrix A is an m by n, that means it has m rows, row 1, row 2, dot, 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 row m. What then is the row space? The row space is the span of these rows, row 1, row 2, dot, 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 row m, right? Now the row space, it's not going to have direct applications to the transformation with the standard matrix that we were just discussing, but it can have some other things that's going on. So firstly, what else can we say here? Well, each row has n entries, right? Because there are n columns, each row has n entries. Well, that means the row space is a subspace of Rn. In other words, the row space is something which is also in the domain of our transformation, right? So we're going to talk more about this tomorrow. And then the last thing I want to highlight here, and this could be helpful for some of the homeworks. Oh, and homework 4, I'll post that on Canvas today, so you'll have that. But the last thing I want to highlight is that the row space also equals the column space of A transpose. Why? This seems bizarre. Why is transpose popping up out of nowhere? Well, remember, what does the transpose of a matrix do? The transpose of a matrix is a matrix where the rows and columns are swapped. So what is the column space of A transpose? Well, A transpose says my rows become columns, my columns become rows. So if I'm looking at the columns of A transpose, those columns of A transpose used to be rows of A. So if you're looking at the column space of A transpose, that's really the same thing as the row space of A, because the columns of A transpose are the rows of the original matrix, right? And so we get this nice property that relates the row space and column space together. Okay, good. With that being said, let's go ahead and look at today's participation question. So I'm going to share my screen. Here we go. Okay, looks like it's sharing. Great. We are looking at participation day 14. All right. And we're told if A is a 2 by 5 matrix with real number entries, then what space is the column space of A in? What space is the null space of A in? Well, first of all, remember, what is the null space? Null space is a set of inputs. It's the set of x's. Well, if you have a 2 by 5, your x's must have 5 entries. Well, if your x's have 5 entries, your null space is inside of R5. Well, then what's the column space? It's the set of outputs. So it is inside of R2. So we can answer here. If I go in student view. So what space is the null of A in? The null of A is in, and you can just write it with R and do caret symbol for power. The null space is in the domain. So the null space is inside of R5. What about the column space? The column space is in the output space. right? It's a set of combinations of the columns. Each column only has 2 entries. So these possible outputs are in R2. And so this will give us our answer for today's problem. This is really just trying to highlight the difference between domain and codomain and what the column space and null space have to do with each of them and what spaces they live inside of. All right, so we can hit submit. And that's it for today. By all means, if you have other questions, please let me know. Email me. We can talk about it. Also, I have office hours this evening at 6 p.m. The Zoom link is on Canvas if you'd like to use that to talk to me about anything. Otherwise, that's all for today. Best of luck, and I will see you tomorrow.